Right. Good morning, everyone, or afternoon or night, depending on where you're joining from. I'd like to welcome you all to the session today on model checking and validation, which has six very interesting papers that really span the gamut of what is meant by models, from statistical models to machine learning models. Um, I invite you all to ask questions on Slido, and I will also be monitoring the Discord. But without further ado, I'd like to present our first paper, Beyond Correlation, Incorporating Counterfactual Guidance to Better Support Exploratory Visual Analysis, which will be presented by Arran, Zeyu, Wang. So take it away, Arran.
Thank you so much, Michael, for the introduction. Let me share my screen quickly. Yeah. Oh, hi, folks. I'm Arran from UNC Chapel Hill. The title of my work, of our work, is Beyond Correlation: Incorporating Counterfactual Guidance to Better Support Exploratory Visual Analysis. I'll be sharing this work on behalf of my colleagues from UNC Chapel Hill and the Rinsey Institute. Supporting efficient discoveries of insight within complex datasets is a primary goal for exploratory data analysis. For addressing this goal, guided approaches in visualization become more and more common to help users explore data. Fabulous past work have offered many aspects in guided analysis, including a theoretical framework for practical guidance strategies, using model checks to better support better validation and exploration in visual analysis, as well as using AI-guided supported method as guidance in visual analysis. While the most common guidance metric could still be examining the correlations from data, like this correlation plot, it has also been adopted by many statistical softwares like Systat. While correlation is efficient when exploring data insight, but it may also have some limitations. Look at this chart. It says how insightful oversimplified YouTube video titles are correlates to snowfalls in Chicago. But it doesn't necessarily mean video titles cause the snowfalls. That is the famous statistical mantra. Correlation does not imply causation. Well, in this paper, we combine an idea called counterfactuals. It involves the exploration of hypothetical alternatives to the observed event in which a particular factor is altered. For example, assuming what if you won $1 million in the past. Well, past studies have shown that counterfactuals can help communicate the relationships between variables of interest in analysis. And it can help users understand data even with static charts. In this work, we combine the counterfactual ideas into guidance. Well, for this, we need to first understand how users perform analysis with guidance. Let's go through a very simple example analysis. Assuming we have a data set of students' grades, we want to analyze whether coffee drinking impacts students' grades. What can we do? So usually the first step is we will filter the data, from which we will get an included data set. Here is our point of interest data samples, including all students who drink coffee. Simultaneously, it will create a remaining data subset initially created by the excluded subset contains all students who don't drink coffee. So we can examine students' grade distributions of these two subsets using correlations. For example, here, which is obviously different. So here the correlation analysis actually shows coffee drinking correlates to students' grades. While people may interpret them as coffee drinking causes those different grades, but can we really conclude that? And what is actually causing these differences? To better understand to help answer these questions, we combine the idea of counterfactuals to data subsets. For this, we can create a counterfactual data subset from the excluded data subset. It will be similar to those from the included data subset, while with an alternative filtered value. Here we define similar as they are similar in other dimensions than our very first point of interest filters. In this case, it's coffee drinking. So our counterfactual subset here will include students who don't drink coffee, but they are similar to those who drink coffee in other dimensions. While the rest, we call them remainders. It will contain students who don't drink coffee, meanwhile they are not similar to those who drink coffee. To better understand how it works, let's go back to the very previous example as our first archetypal cases. Similarly, we see a big difference on students' grades between students who drink coffee or not. But if we look at the more detailed subsets, where the counterfactual subsets here on the right up, sorry, it seems to have a similar distribution with the included the data subset on the very left side. This means students who drink coffee or not may have similar grades if they are similar in other dimensions. In other words, counterfactual guidance actually tells you here coffee drinking may not cause the differences in students' grades. And therefore, it can prevent false positive when you may be hinted by pure correlations. But we have 3 data subsets. What about the remainders? Here we can see an obvious difference between the students' grade distributions of the remainders and the included data subsets. It means students who don't drink coffee may have different grades if they are not similar in other dimensions with students who drink coffee. This indicates some dimensions other than coffee drinking may contribute to the difference of students' grades. This is when the remainder subset could be somehow useful in these cases. Well, if we simply exchange the distribution of counterfactuals and remainder subsets, we got a second archetypal cases, as shown here. But in this case, counterfactual data subsets are not similar with included. This means counterfactual guidance could hint coffee drinking may cause the differences of students' grades. Where in this case, we got a similar results with correlation guidance if we were using counterfactuals here. But what if different and probably more complex cases appears? Like we are showing here, if the data subsets look like this, we say both counterfactual and remainders are not similar with included on the very left side. It means the distributions of excluded on the middle depends on how counterfactuals and remainders is combined together. Here, comparing the result, counterfactual guidance could tell us both coffee drinking and some other dimensions may cause the differences of students' grades. However, as we mentioned earlier, the results of correlation guidance could depend on how the 2 counterfactuals and remainder subsets combine together. And it may either lead to similar results of counterfactuals or not. Well, let's see some simple cases where if all the data subsets have similar distributions as we shown here, users may conclude nothing matters, or at least coffee drinking may not matter here. And the results will be similar no matter you're using correlation or counterfactual guidance. Lastly, when all the 3 subsets on the right side shares a similar distribution, but all of them are not similar with the included subset which contains students who drink coffee on the left. In this case, we may conclude both coffee drinking and some other dimensions may matter and contribute to differences of students' grades. Similarly, in this case, counterfactuals and correlations could lead to a same interpretation. And here we show an overview of all these 5 archetypal scenarios with its corresponding potential insights from both counterfactual guidance and correlation guidance in the bottom area. And we highlighted the 2 cases when users may get into a situation that correlation may lead to inappropriate inferences or false positives, while counterfactuals could help users defend such false positives. But we also want to acknowledge that these are not when correlation fails. Probably this may be simply due to when people's judgment of causality from data fails, which hence we may need a deeper look at the data, and that's why counterfactuals could be helpful under such circumstances. Now I think we got a better understanding of those conceptual and theoretical differences, so let's go to a more technical part. Counterfactuals has been utilized by previous work, while in many of them, counterfactual visualizations are shown with multiple charts, mostly combined with included and counterfactuals together, subsets together. But it lacks of simplicity and increases the complexity of users' understanding. So in this paper, we simplify them from charts to guidance values. Because here, as we mentioned earlier, we are not really interested in how much they are similar, but how much they are not similar. So we examine the distributional dissimilarity between included and counterfactuals as part of our guidance values called counterfactual dissimilarity. Similar, we calculated a remainder dissimilarity between included and remainder subsets Therefore, combining them together, we constructed the counterfactual guidance technique. And the formats of counterfactual guidance is like this. It's kind of complex and consider the time limit, so please go to the paper for details. Well, for evaluation, we built up a prototype with two views. One showing guidance information like the overview of guidance values between variables. Another view shows analytical details information like detailed guidance values with different subset distributions. And we generated a synthetic healthcare data sets based on a ground truth color graphs, provided causal relationship judgment tasks for users. And we hypothesized different performance between the two guidance techniques. Like we assume counterfactuals may lead to higher accuracy, higher confidence, fewer wrong attempts as longer times. And we conduct the study using with 20 users, 10 with counterfactual and 10 with correlation guidance. We provided our key takeaways from the evaluation, including first, counterfactual guidance could lead to higher accuracy, where their accuracy is measured by how much users' answers aligns with the ground truth color graphs. And fewer wrong attempts, which is measured by how many users' explorations are not in the ground truth answers. But we didn't find any obvious difference in confidence and any obvious difference in time, probably due to the simplified representation of counterfactual information in our work. And further, we also discussed the exploratory behaviors of users, where we found overall the exploration sessions are likely to be depth-oriented, aligned with some previous insights. And more specifically, we found counterfactuals can lead to even deeper analysis based on the evidence that users have more detailed future explorations using counterfactuals. We identified some key limitations that need to be improved in the future, like we choose some empirical parameter choices, lack of automated filter computation, and synthetic data, as well as test design variable choices or interfaces. This work is not possible without our fabulous co-authors, and it's supported by NSF. Thank you so much.
All right, thank you, Arran. While we're waiting for questions with the tape delay, I'll ask one.
Thank you.
Yeah, which is that so to me, kind of the main one of the main takeaways from your work is just how dangerous exploratory data analysis can be, right? You're confusing correlation with causation and all of these things.
Yeah.
And I kind of wonder how just sort of the central insight of selecting important subsets might be used not just for counterfactual generation, but other ways of making EDA safer, right? So the notion of like separating a train set from a test set or doing cross-fold validation on insights, right? So are there other tools that the system could use to sort of bridge this exploratory, confirmatory data analysis gap?
So I think there may be some other subset-based analysis. For example, there's a propensity score matching method in the causal analysis community, a statistical causal analysis community, where they also did some analysis by splitting the data into different, likely different subsets or different partitions to better understand the correlation between specific data subsets. I assume those kind of approaches, and also those kind of approaches actually depends on, like what we said, we are a preliminary study, and it depends on the specific types of data or specific tasks that you can use, because in this work, we use Euclidean distance as our default measure, but there could be a lot more measurements, distance measurement like homologness and Hamming distance probably. And so I think this could also be related to what your specific task and your specific data set is. And then you need to choose specific different types of probably measurements and different types of, as what we said, like those, like here we have some empirical like value choices in the computation. So those values can even be changed if your task or your data set could be somehow different. And I think it really depends on what you are really analysis. And this is also part of our current goals, which is to provide a better usage guidelines for counterfactual guidance under different circumstances. Yeah, thank you so much.
Yeah, and one more question coming in from Slido, and then we'll have to move on, unfortunately. But are there other data relationships that this could be applied to other than causality?
Yeah, I think there could be, because counterfactual guidance is actually built upon correlation. So, but I assume there will be a lot more other relationships that can be examined here. So I think probably we can discuss more on Slido, on Discord, because it's quite a complex problem currently for me to give you an overview of all potential distributions of data, I assume. Yeah, thank you so much.
Yeah, I have plenty more questions, but unfortunately we're out of time. So let's move on. Let's thank our speaker, but move on to our next paper. which
Thank you so
is
much.
beware of validation by eye, visual validation of linear trends and scatterplots. That'll be presented by Daniel Braun.
Yeah, thanks for the introduction. I'm Daniel Braun from the University of Cologne, and this presentation is about the visual validation of linear trends in scatterplots. The paper is the result of a collaboration together with Tatiana von Landesberger, Remco Chang, and Michael Gleicher. The motivation for our work was that validation in general is an essential part of building regression models. But often, statistical analysis alone is not sufficient to validate model results, and an additional visual testing is needed. Examples for this are the dinosaur data sets or also Simpson's paradox. And when we looked at the literature, we saw that the visual estimation of linear trends has been widely researched in the past, but visual validation remained under-investigated. Therefore, we aim to answer the following two research questions. First, how does the performance in visual validation of linear trends relate to the accuracy of visual estimation? And second, whether common visual designs can enhance the performance of visual validation of linear trends. To answer these questions, we conducted two user studies following a similar design. For each trial, we generated 100 data points equally distributed on the x-axis using standard OLS regression models. The resulting y-coordinates were afterwards permuted by normal distributions, and all the trends we showed were centered in the middle of the scatter plots. So in this work, we focused only on the slope parameter of the trends to be validated and estimated. To test the visual validation, we showed the participants trend lines with slopes deviating from the true trend line. The respective stimuli were created by quantifying the deviation of the shown slope as the deviation from the true slope as a proportion of the standard error. In the first experiment, we compared humans' ability in visual validation and estimation in a between-subject online study. The first group of participants only saw the raw data and had to estimate the linear trend of the data points by their own. The second group was shown pre-drawn trend lines in addition to the raw data, which the participants had to either accept or reject as the true trend of the underlying data. The analysis of the first experiment revealed two main results. First, the participants were more accurate in estimating linear trends than in validating them. This can be seen by comparing the cumulative distribution of the estimation errors with the acceptance rates of the validated lines. In the figure you can see here, the x-axis indicates the deviation of the estimated and validated slopes from the true trend, and the green line shows the border of the true slopes 95% confidence interval. And as you can see in the figure, participants not only accepted fewer correct models than they estimated, but also accepted more incorrect models than they estimated. As a second result, we found a validation bias towards too steep trend lines. That means that trend lines with an increased slope got much more likely accepted than ones with a decreased slope in relation to the true trend. Both results are nicely illustrated in this example stimulus by comparing the mean validation acceptance range, which is marked as the orange area, with the mean estimate and the actual true trend. The validation acceptance range not only exceeds the mean estimation, but is also way steeper than the true trend. In order to find a possible reason for the too steep bias, we conducted a post-hoc analysis comparing the responses with both vertical OLS regression and orthogonal ODR regression as the assumed true model. While OLS regression assumes errors only in the y coordinates, ODR regression assumes errors in both coordinates. And given the improved accuracy in relation to ODR regression, as you can see in the figure on the right, that indicates that participants naturally assessed ODR regression rather than the common OLS regression. As additional results, response times were significantly lower for validation, but the estimation task was perceived significantly easier by the participants. Given the relatively bad results for visual validation in the first experiment, we tested in the following whether incorporating common visual designs to show the model results would support the visual validation. We used the same structure and the same data as in the first study and tested 3 designs. The OLS error lines, you can see on the left, a bounding box in the middle, which was created by shifting 2 lines parallel to the shown trend line outwards until they reach the outmost points, and the standard 95% confidence interval on the right. The results of the second experiment show that the error line design was the only one reducing the too steep bias we found in the first experiment. But unfortunately, none of the designs led to the desired general improvement in validation accuracy. So given our results, there are many possibilities for future work. For example, it would be interesting to investigate whether our results also apply with an increased model or data complexity, and based on the results of the second experiment, additional research on the visual design for showing the regression models is needed. So in summary, we conducted 2 crowdsourced user studies to test humans' ability to visually validate linear trends in scatterplots. We found that people are more accurate in estimating trends than in validating them, that there is a too steep bias in visual validation, and that standard visual designs for showing model results do not enhance validation performance. So overall, our findings suggest caution when using visual validation of regression models. Thank you for your attention, and I'm happy to answer your questions.
Thank you, Daniel. I was going to ask you a question, but we have some coming in from Slido as well. So I'll try to combine them in the interest of time. So one is about the elicitation. How did you ask people to estimate these trend lines? And then sort of related to that, can you speculate a little bit about why people thought the validation task was more difficult than the estimation task, even though they were doing it faster?
Mm-hmm. So to answer the first question, so the estimation task was set up in a way that people saw the raw data and then had a slider to adjust the slope of the trend line, which was then visualized at the moment they moved the slider. And the second question, so why was the estimation task perceived easier? It's a good question. I mean, the lower response time for validation makes sense because they just had to accept or reject a model. But yeah, the perception of the estimation task to be easier is definitely something we have to look into in future work. I mean, it's an interesting finding, and yeah, we should follow up on this in additional research.
Right, thank you. I will furiously type my question into Discord later, but I think unfortunately we have to move on to the next speaker.
Thanks.
So thank you again, Daniel. Our next paper is VMC, a grammar for visualizing statistical model checks. It's going to be presented by Ziyang. So Ziyang, take it away.
Thank you, Daniel. Okay, so hi everyone. My name is Ziyang. I'm a PhD student from Northwestern University. This is my joint work with Alex Kale, who is from UChicago, and Matthew K, and my advisor, Jessica Hullman. They're all coming from Northwestern University. So visualizations play a critical role in statistical workflow. If you're familiar with statistical modeling, then if I'm giving you such an example linear regression model with one predictor, then definitely first you will try to do some numerical model checks, like you want to calculate the R-square value, and if it's high, then tells you that the model fits to the data well. But such summary statistics can hide important information for doing model checks. There are still many questions calling for doing graphical model checks. For example, you might want to check some specific model assumptions like heteroscedasticity by drawing a residual plot, or you might want to check whether a model is reproducing some specific features of the observed data. For example, you can draw a density plot to check whether the tail of the model distribution is fitting to the tail of the observed data. So in this talk, I'm interested in helping people generate graphical model checks, which is defined as a visualization to facilitate the comparison between the observed data and the predictions under the model. And such graphical model checks can take many different forms. For example, in our previous slides, I show an example of the residual plot, and it can take a lot of different forms. Like users can choose to use the intervals to encode the uncertain information in the residuals, or they can use animation to show different samples at a different time frame. And they can also calculate the quantiles of the residuals and compare that to a quantile of a normal distribution to draw a QQ plot. And for another example, a simple example of the density estimation, it can also take so many different forms. But in contrast with such a wide space of model check visualization, the current tools are very limited for helping people compose these visualizations. And users are heavily relying on their previous experience to guide their design choices. And we see this situation is limiting users' exploration of different model check visualization, such that they don't get a good understanding of the design space of model check visualization. So in our paper, our goal is to develop a grammar to facilitate visual model checking. And we want to deal with the trade-off between the expressiveness and simplicity, which means that on the one hand, we want to cover the design variations and as many as possible. And on the other hand, we want to simplify the grammar specification so that we can only contain the meaningful abstraction to model check visualization, such that we can encourage the exploration of the design space of model check visualization. So our contribution is that we propose VMC, a declarative grammar with components tailored to the design variations of model check visualizations. Okay, so a model check visualization specification in R language might look like this. It looks like very long, and we want to identify the key components and design choices that may result in different model check visualizations, such that we can abstract out the key components and such simplify the generation of model check visualization. So here is a distillation of the key steps in a workflow for generating model check visualization. First, the author need to access the information in the model and to sample it, to sample the data from distribution. And user also might want to do some transformation on the observed data before putting that in the visualization such that the comparison is aligned. And then the user want to generate the visualization for model samples and for the observed data. And lastly, they want to compose the two visualizations such that it can facilitate the comparison between the model and the data. So our grammar builds four main components upon these key steps, and we try to cover the mean variations of different model check visualizations in those four steps. The first step is sampling spec. It covers the variation in the method of generating samples from the model. For example, in our grammar, user can choose which model quantity they want to generate some samples from and which input data set they want to use or the number of samples they want to generate. And the data transformation is a function that user should specify to do the transformation on data. For example, user can choose to rescale the data so that the unit of the data is aligned with the model's output, or user can choose to filter out some outlier in the data set, or they want to aggregate the data before putting that in visualization. And for the visual representation, we use 2 dimensions to cover the key variations in this step. The first is mark type, which is which type of visualization you want to use to show your model prediction. And we summarize 3 categories of these mark types from uncertain visualization literature. The first category is called extent, which uses some area or length to encode the distributional information. And the second is visual variable. It's used something like color or opacity to show the distribution. And the countable icon is just use some ensemble to encode the distribution. And then we also propose another dimension is called grouping sample. It encodes the users' different choices in putting the samples in to the mark types. So user can choose to collapse all the samples in one mark, or they can use individual marks for each sample, or they can animate to show a sample and a time frame, or they can aggregate the samples into one result first before putting that to the mark. And the last component is comparative layout. In our grammar, we summarize 4 different ways to construct the comparative layout from visualization literature. The first is superposition. It's like user is choosing to overlay the model prediction and the observed data in the same plot. And second is juxtaposition, to just put the 2 plots, one for model prediction, one for observed data side by side. And there's also nested juxtaposition, which means that they want to put the model prediction and observed data side by side within the plot, such that it reduces the visual distance and it facilitates the comparison better sometimes. And the last one is to explicitly encode the relationship between the model prediction and the observed data. For example, in the residual plot, the difference between, the comparison between the model and data is facilitated by calculating the difference between the model and the data. Yeah, and we implement our grammar VMC and the R package. So here is an example of the ring cloud plot that I showed earlier. Its grammar components. So you can see like there are 3 different visual representation layers. It controls the visual layers upon the model prediction and the observed data. For example, this one is that it says that the model prediction should first be shown by a layer of interval plot. And another one said that models should also, there's another layer that the model prediction should be shown by slab plot. And the observed data should be shown by some dose plot. And the comparative layout is nested juxtaposition, put the model and the data side by side within the plot. And this is the implemented R code. In our grammar, you can see it's shortened a lot compared to that GG plot I showed earlier. And also the translation from our model's components to this R code is also very direct. So I already showed that our grammar uses several simple components, but still achieves expressiveness to generate model check visualizations. But there are still some questions unanswered, and I'm going to talk about that later. Now, sorry. First is, could we reproduce the practices of the model check visualizations in real world? And second, that how might using our new grammar can affect the practice of the people who are already familiar with doing model check visualization? Yeah. So to validate our grammar, we collected and reproduced the canonical model check visualization from literature. We first verify that our grammar is expressive because the reproduce the sample set we pick. It covers taxonomy of model check techniques from a statistical textbook. And second is our grammar simplified the code to generate the model check visualization. And we also conducted an observational interview study of our grammar. We recruited 3 experienced statistical modeler who deal with model check every day in their life, in their work. And we're interested in 3 questions. First is, does our grammar capture participants' current practice and understanding of model check visualization? And second is, what is useful in our grammar to the participants and what is challenging to them in terms of using our grammar? And lastly, it's like the final question, can our grammar actually help the participants explore new model check visualization? Okay, so the first result from our interview study is that we found our grammar aligns with participants' current understanding and practice. And the participants like the simple specification of a grammar with a few concept of component that covers the variation or the choices of doing model check visualization very well. Second is our participants also recognize the visualization that they commonly use in their practice, like QQ plot or the line ribbon plot. And the second result of our interview study is that we found our grammar helps the experts to explore the new model check visualization. So I will give you an example here, like when doing the line plot over the multi-layer statistical models, the participants found that I never tried this juxtaposition, so I'm gonna try, and he found that okay, this juxtaposition definitely reduces the visual clutter here, and it's much better than the superposition I usually would use. And there's also another question we found in our interview study that we found there's a trade-off between the expressiveness and meaningfulness of our grammar, which means that we found that sometimes the plot generated by our grammar are nonsensical. For example, a participant mentioned that when the observed data is aggregated, probably you should not allow us to apply some continuous mark types because that makes the visualization a little bit weird. Yeah, so I will wrap up with a few takeaways. So our grammar use a small set of sensible abstraction to make the model check visualization easier to reason about and generate. And we think our work paves the way for future research, starting the effectiveness of different approaches to setting up the model check visualizations. And we also call for a systematic design space and software abstractions for model check visualizations. Okay, thank you for your patience. Here's a link to our package and documents. I'm happy to take any questions.
Right, thank you, Ziyang. I also had a bunch of questions on this one, but I don't want to be too selfish. But so the first I asked is, I wonder if you had from your study or just in sort of the prior work leading to this idea of sort of what are the concrete tasks that people have, kind of in line with the previous paper, right? Are they doing these sort of validation by eye tasks, or are there more systematic approaches that they're taking to these visualizations?
Oh, yeah. So yeah, when I started this project, I'm basically looking into the workflow that people would use when they're doing statistical model checks. Like after they fit a model, what is the first thing they want to look at? And like, okay, after they found some problem, how they gonna solve that? So I'll give you an example here. It's like so this is just statistical model. It's just so after fitting the model, the Bayesian statisticians always will show the density estimation that I showed earlier, because it shows a very systematic way to check on the model prediction. And then after they found the problem, they will like, okay, I want to end in the value of predictor first and to check, okay, where is the misalignment between my data and model. And yeah, and that thing could like almost help them solve all the problems they found, like almost help them fix their model. And after they found, okay, model looks very good, like in this visualization that shows the original data, that they will, okay, think probably I want to start check those assumptions like heteroscedasticity I showed earlier, or some or some other like normality of the residuals that also show checked by the QQ plot. And like, yeah, so basically I think there is definitely a systematic way to think about that from statistical modeling. But if we want looked at from a wider perspective, like what can visualization do generally to help people doing model check? So I believe that the effectiveness of visualization to help people doing model check is based on our vision, like the visualization is helping people can reduce the task of checking the deviation from symmetric, and that is very that can be done very well by the human visual system. So I think we can, based on this point, and try to look into a big picture of how visualization can help people do model check. And like, because like human doing model check every day, even though they're just looking at the visualization, just showing the observed data, they're still imagine what is trending here, how can I understand this? So I think people usually understand data through model every day, but just didn't say it out.
Yeah, no, I would can talk way more about this, but unfortunately we have to move on. But thank you again for the presentation. I will leave the slide up just for a couple more seconds if people want to look at those QR codes. But then we will transition to our next talk. So this is Jiayi, who's going to be presenting visualizing and comparing machine learning predictions to improve human AI teaming on the examples of cell lineage. Right. Great, take it away.
Thank you, Michael, for the introduction. Hi, everyone. My name is Jiayi. Today, I'm going to present our paper entitled with Visualizing and Comparing Machine Learning Predictions to Improve Human AI Teaming on the example of cell lineage. This work was collaborated with Maciejewski, Alain, Trubuil, and Tobias Isenberg. From the title, you may wonder, what is plant cell lineage? Cell lineage is the development history of plant embryos. To grow, an embryo needs to keep dividing. One cell divides into two, and two cells divide into four. This video was taken by our implementation. So you can see here how a normal cell would divide. This division process can look like this if visualized in a hierarchical tree. Each level represents one generation, which means all the cells on the same level divide at a similar time. So for an embryo, what do biologists do to build the hierarchy? To get the knowledge, we observe the biologist's working process and discuss it with them. When biologists try to reconstruct the hierarchy, they will first observe the 2D slide from the microscope. As shown here, this is an embryo with 32 cells. Then they would actually build the hierarchical tree from bottom to the top. To be detailed, when building the cell lineage manually, biologists basically need to find the right sister cell for every cell in an embryo. Since only the neighboring cells of a target embryo can be the potential sister cell, biologists need to check the neighborhood of each cell. Once they decided on which cell is the most likely sister cell, they will merge these two cells and continue assigning for the remaining cells. After assigning for this generation, biologists can get a view like this one. Then they will continue this process to the new generation until there's only one cell left. So to summarize, biologists start with the segmented 2D slides from the microscope. Then they check every cell one by one within this embryo. For each cell, they would manually find the right sister cell. When they finished one generation, they will move on to the next generation. They will write down the hierarchy on the paper. As you may know, there are two main challenges during this process. As biologists make all the decisions themselves, the assignment process is time-consuming and tedious, especially for large embryo with 8 or more generations. Apparently, we can seek solutions from machine learning. However, our scenario is a little bit tricky because we don't have enough training data sets, which were manually created by biologists. So we cannot simply create a best model. So how can we deal with such a situation? We decided to involve users to make choices with the help of machine learning. This is the basis of applying human anatomy in our scenario. That is, to make use of machine learning at best. At the same time, we should allow biologists to fully control the final decisions. Let's first talk about how we made use of machine learning to help experts. First, we tested multiple models and picked 5 of them because the predictions of these models are diverse and can cover most cases. These models are support vector machine, random forest, k-nearest neighbors, neural network, and Gaussian naive Bayesian. We pre-trained these 5 models in advance and included them in the website. Biologists can also retrain these models with the system before loading a new embryo. Then we use the cross-validation approach to get the accuracy rate and record rate of each model. And we visualize them in the group stacker bar chart. We also listed all the features we used in the training the models and allow biologists to customize the feature they wanted to retrain the models. Through this method, we can minimize the limitations one single model could bring. Also, biologists could compare these models by visualization and decide on their own later which model to trust more. With the predictions from 5 models, we visualize them in different layers. Let's take the subtree cell N-8 as an example. All the children cells of the parent cell are listed below. They are displayed from left to right based on model confidence. The least confident prediction is placed on the very left so that biologists can check first. We visualize such confidence by the color of horizontal bars. The more black the bars are, the less confident models have for this pair. You may know that there are 2 special cases, cells 31 and 19. They have type texture, and it indicates that these 2 children cells were predicted with no sister cell in this generation. We also get and combine all the predictions from 5 models and visualize with stacked bar charts. We place the bar chart on the side of each node close to their proposed sister so that biologists can have a better understanding of the overall predictions. But this single view actually is not enough. Biologists may want to know the detailed prediction of a specific cell. We designed that when biologists double-click a specific cell to have a detailed check, for example here, double-click the cell 9, we will show the detailed prediction from 5 models for this cell. As you can see in this figure, 5 models propose 3 sisters, 23, 8, and 19. Their proportions correlate with vertical thumbnail of all the predictions. The gray area visualizes the uncertainty of the model, since no model can reach 100% accuracy rate. For all the other neighboring cells, we display them below the target cell, just in case none of the proposed sister cells are satisfying for biologists. We also enable biologists to hover over one model to see which pairs are predicted by a specific model. For example, here, when hovering over random forest, all the pairs predicted by this model will be highlighted with red strokes. Another solution is to allow biologists to fully control the final decisions. We first imported the concept of model weight. By switching the model weight, biologists can change the proposed sisters for each cell from the model in the beginning and the visualizations of predictions. This allows them to incorporate their preferences into analysis by simply changing this value. Secondly, all the views of model predictions are linked together. If we take the prediction from each model and times with specific model accuracy rate and model weight, we will get this view. After scaling, we can get corresponding vertical bar charts on each node like this one. Thirdly, we distinguish the pairs of totally manually assigned, confirmed, manually corrected, and predicted but not checked use the color of horizontal bars. With such an overview, users can track their current progress and see the proportion of their confirmed predictions with manually corrected ones. We recruited 6 biologists who had experience with cell lineage constructions to participate in our evaluation study. We started with a training session letting biologists to get familiar with the visualization and interaction using a 16-cell embryo. Then we conducted an observation study to let biologists conduct cell lineage for a 64-cell embryo. We also performed a post-study interview asking about their experience. The results from the study are as follows. First, all biologists appreciate the prediction results and their visualization. They thought Lineage D+ could help them save time and change their traditional approach they used when they assigned plant embryos. One biologist expressed that interacting with machine learning made her feel like she was discussing with a computer in making decisions like discussing with a colleague. Thank you for watching, and here are materials for reference if you are interested. Finally, I'm also on job market this year. Feel free to reach out. Thank you.
All right, thank you, Jiayi. Just one quick question, since we're behind time a little bit. I wonder the extent to which the data and the tasks in your system might change as particular approaches, machine learning approaches to this problem get more robust, right? So I'm thinking of proteomics, where in a very similar situation, there were lots of proposed models that each had different trade-offs. And then you had AlphaFold come in and, blow all the other ones out of the water. So I'm wondering sort of if, like, for instance, deep learning approaches are things that might have much different patterns of error or superior performance across a lot of these things, if that changes how the system might be used.
I would say yes, like importing another model may change the visualization itself, but we need to keep in mind that because of the limitation of our training data sets, I believe we have just several, I would say maybe 20-ish training data embryos that were previously assigned by biologists, which can be the Braun tubes. And so none of these models can perform, I would say, perfect in finding the right sister cell for a specific cell. So we can import another model, and by using kind of changing the model weight, we can induce our trust in these different models in visualization and see later like which model can perform better and finally get a relatively reasonable divisions.
Great, thank you. There's a couple more questions on Slido that will get pasted in the Discord, so I encourage you to take a look there. But we have to move on to the next one, so thank you, Jiayi. And we'll move on to the next paper, which is Compress and Compare, Interactively Evaluating Efficiency and Behavior Across ML Model Compression Experiments. And this is going to be co-presented by Angie, Boggust, and Venkatesh Sivaraman. So go ahead and take it away.
Thank you so much. My name is Venkat. I'm a PhD student at Carnegie Mellon. And as Michael said, I'm presenting this with Angie at MIT and on behalf of our collaborators, Yannick, Donghao, Dominic, and Fred at Apple. I'm really excited to share this work, which is a tool for interactively evaluating machine learning model compression. So machine learning models can unlock new ways for technology to enhance our daily lives. And also, as you're probably aware, these models are becoming increasingly large and complex and require huge amounts of computational resources to run to enable those experiences. So it's becoming increasingly important to be able to run machine learning models on devices with relatively constrained resources, like our phones, laptops, and smartwatches. So this can help protect users' privacy, enable smoother, more interactive user experiences, allow users to access ML models without an internet connection, and even reduce the environmental footprint of AI. But to gain these advantages, machine learning practitioners are faced with a challenge. If a model is too big, we need to find ways to shrink the model to run more efficiently with less resources. So model compression is a set of techniques to reduce the computational burden of a model without significantly affecting its performance. There's a variety of techniques in the machine learning literature to compress models, including quantization, or reducing the precision of each weight to take up less space, pruning, which is zeroing out the less important weights, or distillation, which is training a smaller model to mimic the behavior of the bigger one. And so by applying all of these techniques in combination, ML practitioners aim to optimize a bunch of metrics at once, like accuracy, storage size, power usage, latency, and others. But as you can probably imagine, balancing all of these criteria with all of these different techniques is a highly complex task, and there aren't currently good ways to help practitioners explore the space of compression techniques and metrics. So this poses an opportunity for a visualization system to help. So we addressed 4 main challenges in our system. First, identifying the optimal set of compression strategies to apply requires a lot of time-consuming and task-specific iteration. So for example, if we take model A, prune it, and then quantize it, we might get a great model, yay. But if we take model B and apply the same techniques, we might get much worse accuracy. But maybe if we adjust some hyperparameters and add a calibration step, we can recover that accuracy. So finding the right recipe for compression is really important and difficult. Second, compression requires practitioners to make trade-offs across the many metrics we saw earlier. So teams often use charts like the ones shown here to compare several models, but to choose one model, they often have to compare across several of these charts while negotiating the project's requirements. Third, once we found some compressed models that work well, we need to evaluate whether they preserve the ways the original model behaved. And what can happen is that maybe our original model makes some misclassifications that we're okay with, but then the compressed model might make the same number of misclassifications, but might now be biased against a certain subtype in the data. And existing tools help us evaluate the efficiency of these models, but it's harder to dig deeper into the behavior that might change due to compression. And finally, compression can have unintended effects on model internals that are hard to debug. So if we look at a generic neural network and now we try to zero out some weights, we might find that the activations downstream of those zeros are completely different. But sometimes this breaks the model's output and sometimes it doesn't. So figuring out what compression caused this breakage can be technically very challenging. So to address all of these challenges, we developed Compress and Compare, which is an interactive system with 3 major components. So let's jump right into a demo to see how it works. Here we've imported an experiment where we tried many different methods of pruning and quantizing a ResNet model for image classification. So the model map, which is this node link diagram on the left, shows each model we've built as a node in a tree. And the color indicates the model's accuracy, while the size indicates the model's storage footprint. The node at the very left is the base trained model, and all of our compression variants stem from that. This visualization allows us to see some important patterns, like the first 3 branches coming out of the base model seem to lose accuracy that we can't recover, while the second set of 3 experiments seem to work better. And the model at the very bottom, which uses quantization only, appears to be both accurate and small. But there may be other metrics we'd want to look at. So let's go to the model scatterplot in the top right and plot the models according to their latency on the x-axis. Now we can hover and brush on this chart to see that most of the models have overall pretty similar latency, except for, again, the quantized model, which seems to be much faster as well as smaller. So quantization is probably a must-have for this particular model. Now, if we want to compare metrics between a subset of our experiments, we can select them in the model map, and the sidebar will automatically figure out what properties of the compression techniques varied between those models, and it'll generate plots that map the X and the color encodings to the appropriate variables of our experiment. So this mapping requires a somewhat non-trivial iterative algorithm, but in our user study, we found that people were kind of pleasantly surprised by how natural this type of experiment plotting was, and it gave them an ability to just look at subsets of their experiments more easily. So check out our paper if you're interested in seeing how that works, or happy to discuss it. Now, in addition to the top level metrics, compress and compare helps us look at differences in the instance and level and class level behaviors of the compressed models. So let's select a few models here, and then we can jump into the behaviors view, which now gives us a class level performance metrics on the ImageNet dataset. So we can select from different metrics here, including the model's confidence on the true label, its correctness or accuracy, as well as other metrics. So for now, let's choose correctness. And here we see the overall accuracy for each class in ImageNet. We can also look at the change in accuracy and and sort the view so that we see the classes that have dropped in accuracy the most. And we see that the Stove class, interestingly, seems to have lost accuracy for both the quantized and the pruned models. So if we click into those, we see that these might be hard examples that the model has forgotten how to distinguish after we compressed it. So why does pruning result in some models doing much worse than others? We can select some models and go to the layers view now, which now shows us how the sparsity of those models is distributed across the different layers and components. We could also use this view to look at the weight values or the internal activations at the component level, and this can help us find bugs and ways that we could improve the pruning strategy. So together, all of these features help practitioners build a deeper understanding of how compression has affected their models, and it also gives a sense of what experiments they might want to try next. So now I'll hand it over to Angie to talk about how we evaluated the system.
Thanks, Venkat. To evaluate Compress and Compare's ability to support real-world compression workflows, we conducted both a user study alongside compression experts and used our system to replicate and improve upon common compression tasks from the literature. So let's take a look at how Compress and Compare can help us do one of those tasks, which is debug a failed compression experiment. In this scenario, we'd like to run a generative question and answer language model, but we have limited computational resources. So compressing it down will help us reduce its size and improve its speed. Our original large model performs quite well. So given the question, which NFL team represented the AFC at Super Bowl 50, our model correctly responds with the Denver Broncos. However, if we even apply a small amount of compression, it completely breaks the model's generative capabilities. Pruning 10% of the model's parameters causes the model to respond to that same question with Super Bowl 53, 53, 53, 50, 50. And if we prune 30%, it causes the model to produce completely meaningless outputs like AAAAA. But just looking at these quantitative results, it's not clear why compression has had such a detrimental effect. It could be that our model has low capacity for compression and is already as small as it possibly can be. Or perhaps pruning isn't well suited for this model architecture or this task. Or maybe there's an issue in how we've applied our pruning strategy. But we can use Compress and Compare to figure out which of these three things is happening. Compress and Compare's layers view shows us how pruning has changed each layer in the model. We see that the layers that have changed the most are all normalization layers. In our model, normalization layers are really important because they ensure a consistent activation distribution throughout the model. So if we were to over-prune them, we could end up with unexpected results. And we can test if this is actually what's causing our model's poor performance. So we restore the normalization layers in our compressed model, which effectively unprunes them. And while this model was previously the one that produced AAAAA, it now produces the correct response, Denver Broncos, once we've restored its normalization layers. So with this knowledge that normalization layers shouldn't be compressed, we can actually design even better compression experiments, and we can end up compressing our model up to 35% with less than an 8% loss in performance. So here, Compress and Compare has supported us through every step in this compression debugging process. It helped us identify that our experiment failed, uncover the reason for that failure, and build intuition that helped us design new and better compression experiments. Today, we've talked a lot about why compression tooling is needed and how we designed Compress and Compare to support those needs. But during our design process, many of our seemingly compression-specific design choices also felt relevant to general machine learning tooling. For instance, tasks like bridging data and model-centric evaluations, negotiating trade-offs between multiple quantitative metrics, tracking model provenance, and comparing differences across many models were unsupported tasks that compression practitioners needed, and were part of the reason that we designed Compress and Compare. But these are tasks that are also relevant to general machine learning workflows. So in future work, considering these tasks in general machine learning tooling could help not only produce machine learning tools that better support compression, but also improve machine learning tools across all types of tasks. So to summarize, in this work, we've synthesized real-world challenges that experts face in model compression, developed Compress and Compare, an interactive visualization for compression experiment tracking, and evaluated it in an expert user study and case studies on common compression tasks. This is actually the third paper in a series on visualization and compression from Apple. So if you're interested in this topic, be sure to check those out. Thank you so much for joining us today, and we're very excited to chat more about Compress and Compare.
All right, thank you both. One quick question from Slido, which is, what does significantly mean in terms of false negatives and false positives in terms of accuracy and consistency?
Is that
Might be relevant to last paper, but
maybe we could discuss that one more on Slido. Just not sure exactly. I'm assuming they're referring to what we briefly mentioned for false positive and false negatives around image models.
yeah.
There, it depends on the type of compression strategy that you apply. So some, it's been shown in the literature that, you can apply compression and it can have a pretty big impact on your model's behavior that doesn't show up in terms of actual accuracy and performance, but it sort of has this weird impact where the model sort of forgets these sort of tail distribution data that you've trained it on. And that's oftentimes really important, right? Like that's the data that you've really worked hard to collect. That's not, the common data that is easy and exists everywhere. That's the data that represents information you really wanted your model to learn. And so oftentimes those tail distribution knowledge, that tail distribution knowledge is what can be forgotten during compression. And there's lots of examples of that in the literature I'm happy to point to in the Discord.
Yeah, you can take that discussion on the Discord. I will also let you take this discussion on the Discord, which is, as you mentioned, compressing models often smaller subsets are where that performance loss happens. So I wonder if that might impact model fairness, or if fairness metrics might be something you might incorporate into this tool. And then the last maybe stumper is, could you use this tool adversarially to create a model that superficially appears to be the same as the overarching model, but in fact is totally unfair? But I will, that's more of a Discord or over a beer discussion. But we unfortunately need to move on to the last paper, which is Pareto Tracker, Understanding Population Dynamics in Multi-Objective Evolutionary Algorithms through Visual Analytics, and that will be presented by Fan Yang.
Okay,
So
can you hear me?
Yes.
Can you see my screen?
Yes.
Okay, let's get started. Hello, everyone. My name is Fan Yang, and I'm from Southern University of Science and Technology, China. Now, I will present our visual analytics framework on MOEAs. First, let's discuss what multi-objective optimization is. Multi-objective optimization problem involves optimizing two or more conflicting objectives simultaneously. Let's take a look at a simple example. Suppose we have two variables and two objectives as follows, and our goal is to minimize both f1 and f2 at the same time. With constraints for x1 and x2, the decision vectors outline the decision space like this. After the entire decision space has been fully exploited, the objective space is gradually covered. Notably, there are some outstanding solutions on the left bottom column. For these solutions, there's no solution better than them in all objectives, and we call these solutions Pareto optimal solutions. and the state of all Pareto optimal solutions is called a Pareto front. Overall, solving a multi-objective optimization problem is equal to finding the Pareto front. Multi-objective evolutionary algorithms have emerged as powerful tool for solving complex multi-objective optimization problems. To understand these algorithms, we need to grasp several key concepts. A generation refers to a single iteration in the entire process. An individual is a single solution vector that represents a potential solution to the problem. The population is a set of individuals in a single generation. The evolutionary operators such as mating, crossover, and environmental selections are techniques that are used to create new individuals and select the best solution for next generation. Starting from randomly generated individuals, the corresponding solution sets in the objective space keep getting closer to the Pareto front through generations. To understand the details in the evolutionary process and design decent visual representations, a typical pipeline of MOEA can be illustrated as the following chart. First, the algorithm will select individuals from previous generations' population to build a mating pool. After crossover, the decision space are exchanged and making a new group of offspring individuals. Some of these new individuals will experience random mutation. Finally, all of the individuals in this process will go through environmental selection, leading to a new population of next generation. Although there are some visualization methods available in the third-party libraries like PyMo and PlantEmo, it's difficult to modify them flexibly to meet different needs. Most of the existing works are static visual representations, which requires a high level of programming skills and do not support dynamic comparisons between generations. Some visual analytic frameworks have tackled this issue of analyzing MOEAs. However, in-depth examination of the operators is still lacking. Guided by a literature review and expert interviews, we identified 3 levels of key requirements and analytical tasks. First, we need to understand overall quality measures to identify key evolutionary behaviors. Then, we need to freely explore the dynamic changes of individuals across generations. Finally, at the most detailed level, to understand the evolutionary process, we need to inspect each operators. To meet the requirements and these tasks, we designed the corresponding visualization modules, ranging from overview to detailed insights. Now, let's take a look at our multi-level visual analytic framework. As an entry point, the performance overview displays the trends of 4 quality measures, and the stacked bar below depicts the proportion of different types of individuals. User can select an interested range of generations. The objective space and the decision space are shown in the main workspace from left to right. Users can inspect an individual and its lineage tree. Details of the lineage tree are illustrated in the lineage view. In-depth analysis in the evolutionary operator view consists of 3 panels: the mating and crossover panel, the mutation panel, and the environmental selection panel. And I will introduce more visualization and interaction details in the following case study. Here, I will briefly introduce the performance of SMS EMOA algorithm on the real-world optimization problem, DDMP2. And we set the population size to 100, and the algorithm runs for 500 generations. In this case, we identified 2 individuals that made great contributions to the overall population and explored their lifetimes. HV and IGD show relatively monotonic trends towards optimal, while MS and SP fluctuated and then stabilized around 40th generation. The decreasing number of mutated individuals in the stacked bar confirms that. A remarkable rise in MS and SP is observed between the 50S and the 87th generations. In the 59th generation, the emergency of a mutated individual is noted, broadening the solution set coverage. The lineage view shows that it doesn't survive beyond the 71st generation, while MS and SP remain elevated. In the 71st generation, a nearby individual, number 7054, takes over the role of that spatial one and dies in the 87th generation, validating the rise of MS and SP value. To understand the emergency of this spatial individual, the evolutionary operator view of the 59th generation is inspected. In the mating at crossover panel, the result of the crossover operation doesn't occupy its position. In the mutation panel, the mutation operation propels it toward top left. However, the increasing of reference point distance may indicate that it's getting worse on some objectives. Focusing on the environmental selection panel, the individual ranks second in the first group, indicating that its contribution to the overall solution set quality. Turning to 87th generation, the latter spatial individual falls into the second group in the environmental selection, indicating that it's dominated by some individual in the first group. In summary, we propose a visual analytic framework for inspecting the dynamic and evolutionary process of MOEAs, together with a suite of visualization and interaction designs. In the future, we intend to improve the capability with decomposition-based algorithms, extend our framework to plugin-based environment, integrating application-specific information, and extend it to a broader audience. More details are presented in our paper. Thank you for listening.
Right, thank you, Fan. Unfortunately, our stream turns into a pumpkin in, I think, 2 minutes. So we'll get cut off. But so maybe you can take this question to Discord, but we have at least one wondering sort of, given the sort of non-deterministic nature of some of these evolutionary algorithms, are there ways of sort of going from patterns noticed in your tool to actions taken next? And again, unfortunately, we won't have time for you to actually answer it live, but you can maybe discuss it in Discord. But in general, I just want to thank all of our speakers today for some really excellent papers. And I hope to continue this discussion on Discord. So let's thank Fan specifically, and then all of our speakers in general. And I will see you all soon.